Hey, good morning, guys. So today we're going to pick up where we left off, talking about trig integrals. You switched over to the .cam. Okay, so last time we saw how to handle the sine cosine integrals if at least one of the powers is odd. I worked two examples for you, and in both examples, one of the powers was odd and the other power was even. I want to talk to you today about what to do if both powers are odd or if both powers are even. If both powers are odd, then the same method we use will work. The same method we used on Monday will work. So picking back up with integrals of the form or you can use the variable x or theta. I think we're actually using the variable theta on Monday, but of course it doesn't make a difference. So if at least one of m or n is odd, we will set aside one copy of the odd powered function with the differential and substitute for the other function. So if the power of sine is odd and the power of cosine is even, then you'll take one copy of sine, set it over here with the differential. What's left will be an even power of sine, which you can rewrite using the Pythagorean identities in terms of cosine, and then you'll substitute for cosine. If both powers are odd, though, then you have a decision to make. The other attack here is if both m and n are even, then we use the identities sine squared theta equals 1/2 1 minus cos 2 theta and cos squared theta equals 1/2 1 plus cos 2 theta until we can integrate, i.e. until all the powers are gone. Okay, so come back and look at one of these where both powers are odd, and we'll see that there is a little bit of wisdom in picking which one to substitute for, and then we'll look at these. The other integrals we need to look at, of course, are the secant tangent integrals, and we will get there. So here, let's look at sine to the 9 theta times cos cubed theta d theta. Here, I'm definitely in that first case. because it is true that at least one of the powers is odd. They're both odd. So I have to choose which one of them I want to set aside a copy of with the differential and which one I want to substitute for. If my goal was to substitute for cosine theta, then I would set aside a copy of sine, because the derivative of cosine is negative sine. If my goal was to substitute for sine theta, then I would set aside a copy of cosine. In either case, once I've set aside a copy, the power that's left will be even. Either I'll have sine to the 8 theta here, or if I set aside the cosine, I would have cos squared theta there. And those will be things I could rewrite in terms of the other function for my substitution. So let's try subbing for cos theta, which means set aside a copy of sine. And we'll see what happens. And then we're going to try the other way. If I set aside one copy of sine theta, then what's left here is sine to the 8 theta cos cubed theta, and then sine theta d theta. I could substitute z equals cos theta, then dz would be negative sine theta d theta, so I'll have a negative come out. But before I'm able to make that work, I need to rewrite sine to the 8 in terms of cosine, which is not going to be easy. It is possible, but it's not super easy here. I'll mute everybody by default. And then that way, if you need to talk, you can just hold your space button, space bar. So before I'm able to make the substitution, z equals cos theta go through, dz equals negative sine theta d theta, I need to rewrite these 8 powers of sine in terms of cosine. So here's the trick, right? We're going to use the Pythagorean identity. Sine to the 8 theta is sine squared theta all raised to the 4th power. And then I've got my cos cubed theta sine theta d theta. And this I can write as 1 minus cos squared theta to the 4 times cos cubed theta times sine theta d theta. And now I'm ready to plug in my substitution. So I can't do this substitution until I've just got a bunch of cosine stuff and then sine theta d theta there. So under that substitution, this integral would become the integral of 1 minus z squared all to the 4 times z cubed times negative dz. So I'll bring the negative out front there like that. Does everybody see how we get to this integral at the end? Take a second, make sure you follow this, make sure you could synthesize this, make sure you understand what we did. The big deal is that once you grab one copy of this odd power sine to set over here, what's left is an even power. So since this is sine to the 8, I can write it as sine squared to the 4, right? 2 times 4 is 8. And then this sine squared I can write as 1 minus cos squared. That's the Pythagorean identity. Sine squared theta plus cos squared theta equals 1. So as long as what's left over is an even power, I can always rewrite it in terms of the other trig function.
I have a question.
Yes.
So the last integral that we get, is that equal to the first integral that they ask us to solve?
Yep.
They're equal. It's the same thing.
This is equal to this under this substitution. Yep.
Okay.
I'm going to stop here and see what happens if we do it the other way. So period. What if we try subbing for sine theta, i.e. we're going to set aside a copy of cosine. So I'm beginning again with sine to the 9 theta times cos cubed theta d theta, same integral as the first time, but now I'm going to try attacking it this other way, because according to what we set up here, we could do either. So if I set aside one copy of cosine, then I'll have sine to the 9 theta cos squared theta times cos theta d theta. And now that cos squared I can write as 1 minus sine squared. So this is sine to the 9 theta times 1 minus sine squared theta times cos theta d theta. And here I let z be sine theta. I was going to try to substitute for sine theta. dz is cos theta d theta. So here's my dz. And what I get out of this is the integral of z to the 9 times 1 minus z squared dz. You tell me, which one of the integrals is harder, the first integral or the second integral? So Fernando is getting at what we want to get at. Yeah, the first is definitely harder. Sorry, my cat is stealing my other cat's food. No, no, I know, I love you too, but you cannot have that food. It's not yours. It's just not. Go on. I'm sorry, Keith. Yeah, the first integral is much harder because I would have to multiply out this 1 minus z squared to the 4. That's a pain in the ass. Here, I just have to distribute the z to the 9. So either one will work. Either will work. But the second approach is better. And I could modify that original problem to sine to the 901 or 1009 if we had integral sine 2009 theta times cos cubed theta d theta. Then this guy would end up being a huge thing to multiply out. And sub for cos, we get, well, what would we get? We'd have sine 2008 theta cos cubed theta sine theta d theta z equals cos theta dz equals negative sine theta d theta. So this would have to be sine sine squared theta raised to the 1004 times cos cubed theta times sine theta d theta. So we would end up with, this is 1 minus cos squared, so this would be 1 minus z squared raised to the 1004 times z cubed times negative dz, versus if we sub for sine, we would get sine 2009 theta cos cubed, I write as cos squared theta times cos theta, which would lead to sine 2009 theta times 1 minus sine squared theta cos theta d theta. And then if I sub z equals sine theta here, I get z to the 2009 times 1 minus z squared times dz, which is much, much nicer, right? Comparing this integral to this integral, here you have to FOIL out this massive, massive power of 1 minus z squared. Here you don't. So what Fernando said is correct. If both powers are odd, the power of sine and the power of cosine are both odd, you want to substitute for the larger power, which means you're going to set aside a copy of the smaller power. And that saves you ever having to multiply something huge like this out, right? Which nobody wants to do. It's not so bad if this is a 3 or a 4, you know, it can get a little bit unpleasant. But if this is enormous, then this becomes algebra hell. So I don't want you guys to put yourselves through algebra hell. If both the powers of sine and cosine are odd, substitute for the larger power. And that covers all of case 1. If at least one of the powers is odd, set aside a copy of the odd-powered function with the differential and substitute for the other function. You'll need to use your Pythagorean identities to rewrite whatever's left of the other function in terms of the first one. But it's not too bad. And then if both are odd, my advice is to substitute for the larger odd power. So next we need to talk about what to do if both powers are even. And the best way to get started here is with the example integral cos squared theta d theta. All right, there we go. So integral cos squared theta d theta, there's not much at a glance that I can do with this. There's no way to make a substitution because there's only one function there. But if I use my double angle identity, my half angle identity, I can rewrite that as 1/2 1 plus cos 2 theta d theta, which has the advantage of getting rid of the power. That's the main thing. So these half angle identities that we use knock the power down every time we apply it. Thank you, baby. That's so sweet. From here, I can pop out the 1/2. And then what's left is the integral of 1 plus cos 2 theta d theta. And I can handle each of those on their own. The 1 is going to integrate to a theta. Cos 2 theta is going to be a tiny little substitution. So if you're being very careful about how you write things out, this would be 1/2 integral of d theta plus 1/2 integral of cos 2 theta d theta. And in the second integral, we need to make a little substitution. Here I would let z be 2 theta. dz is 2 d theta. So you're going to have a 1/2 pop out because d theta is 1/2 dz. But we're only making that substitution in the second integral. The first integral doesn't require a substitution. It's easy. It's 1/2 theta. And then I'm just going to write one big plus c at the end. Then I'll have plus 1/2 integral of cos z times 1/2 dz. So I'll get another 1/2 from the substitution. The first 1/2 came from the identity. This 1/2 came from the identity. This 1/2 is coming from the differential term in my substitution. So this is 1/2 theta plus 1/4, and then an antiderivative for cosine is sine. And at this stage, I need to start writing my plus c because I don't have any more integral symbols. And then lastly, I plug in 2 theta for z. So that's how we integrate cosine squared. The integral of sine squared goes the same way. This isn't too bad, right? So then the question becomes, well, what happens if you have larger even powers, or if you have like sine to the 4 times cos squared? These integrals all kind of suck because it's all the same thing. You're just going to do this over and over and over again until you get down to something like that. So I'll do one or two quickly, but then we're going to move on to talking about the secant tangent integrals. Any questions on this problem? Beautiful wife just brought me some Starbucks. My goodness. Coffee and a sandwich. Lucky man. Questions on this? Okay. All right. So then let's look. I could do the sine squared integral, but it goes exactly the same as the cos squared integral. That's not very fun. Let's look at something a little bit more complicated. I'll do two more. I'll do sine squared, cos squared, and then we'll do one of the fourth powers. Things, while they don't get complicated, there's one little step that might require a little bit of thought. This one, however, this one goes really quick. So again, we use, because both powers are even, we're not in that first case, we're in that second case where we need to just use those identities. Cos squared theta is 1/2 1 plus cos 2 theta. And sine squared theta is 1/2 1 minus cos 2 theta. They're very similar. They both end in cosines. The only difference between them is one's a plus and one's a minus. So if I plug both of those in, I get integral 1/2 1 minus cos 2 theta times 1/2 1 plus cos 2 theta d theta. The two 1/2s are both multiplying, so I can bring them together and bring them outside as a 1/4. And then what's left inside is 1 minus cos 2 theta times 1 plus cos 2 theta. I can FOIL that out. It's actually a difference of squares. So that will be 1 minus, see, I'll have minus cos 2 theta from my inners, plus cos 2 theta from my outers. Those will cancel. And I get cos squared of 2 theta from my lasts. Those don't cancel, so we're left with this. And again, I can split it up. This is 1/4 integral 1 d theta minus 1/4 integral cos squared 2 theta d theta. The first piece is easy. How do I handle the second piece? Any thoughts on what I could do with cos squared 2 theta? Same sort of way, yes, but we have to be a little bit careful because the identities up here say cos squared theta equals something, not cos squared 2 theta. But what shows up on the left as the variable is doubled on the right. So cos squared of 2 theta is 1/2 1 plus cos 4 theta. Just replace theta by 2 theta in the original. Yeah, it's very sneaky. All right, so whatever shows up over here is just double whatever shows up over here. So cos squared of anything is 1/2 times 1 plus cos of 2 times that thing, which means cos squared 2 theta is 1/2 1 plus cosine of 2 times 2 theta is 4 theta. We follow that? Yeah, it's a little strange, but it's not too strange. In fact, if you rewrite this original thing as cos squared x equals 1/2 1 plus cos 2x, and then just let x be 2 theta, you get this. So it's very clever use of that identity. It might feel a little bit weird. You did do this in trig. this is how you pass from the original form of the half angle identity to the form I have here. In trig, you started with the form you had here, and the way you got your half angle identity was replacing theta by a over 2. I'm just going in the other direction. Here I'm starting with cos squared x equals 1/2 1 plus cos 2x and replacing x by 2 theta. So this should look familiar depending on how much of the details you remember from that portion of your trigonometry class. This sort of trick is not unheard of. It's something that's done quite a bit. But it is also completely understandable if this looks like crazy bullshit, because we don't do it a lot. But it is perfectly valid. Questions on this identity? Why this is a valid identity or where it comes from? Feels mostly okay? So that first integral is just 1/4 theta, and then I have minus 1/4 integral 1/2 1 plus cos 4 theta d theta. And this is just how we repeatedly break down these things until there's no more powers. What happens is as the power goes down, the coefficient inside goes up. And every single one of these problems, sine, cosine integrals where the powers are both even, is just repeated application of this. You just bash the integrand with this algebra hammer over and over and over again. That's what I mean when I say these are not fun problems. So this will be 1/4 theta minus 1/8 integral 1 plus cos 4 theta d theta. And I don't like to write out the tiny little u sub that you do for the cos 4 theta. I find it much nicer to just do those in my head. So this will be 1/4 theta minus 1/8 integral 1 d theta minus 1/8 integral cos 4 theta d theta. And now the antiderivatives are easy. Cos 4 theta is going to integrate to sine 4 theta over 4, or 1/4 sine 4 theta. And then here's where we add our plus c. You can combine these two terms. And in fact, we could have done all of this work inside of a single integral. 1/4 minus 1/8 is 1/4 though. So this is going to be 1/4 theta minus 1 over 32 sine of 4 theta plus c. So here to here is my little micro u sub, right? I know that the cosine function integrates to the sine function. And I know that the 4 theta, if I substitute for that, I'll just get a 1/4 out from my differential. So we can do those very, very quickly. Over here, I combined 1/4 minus 1/8. That's 1/4. Because this is 2/8.
In the third step from the bottom, what is that next to the theta?
I'm very sorry. I'm sorry. So this is 1/8 when you subtract those. What was the question? I'm sorry. Third step from the bottom. Why did I subtract the integrals? 1, 2, 3. I'm distributing the negative 1/8. So the negative 1/8 is attached to this whole integral. This whole integral is integral of 1 plus integral of cos 4 theta. So when I distribute that negative 1/8, it makes both of them negative. Other questions on this one? So the good news is that all of these go like that. The bad news is all of these go like that. We'll do one more and then we're going to move to secant tangent integrals. let's look at the fourth power of, what did I do? Did I do sine squared or cos squared? Did cos squared. So let's look at the fourth power of sine. And I'm going to try to do this cleanly, meaning I'm going to try to show you kind of an ideal notation. So first, I realize this as sine squared squared, or this. There we go. And then I rewrite sine squared using my identity, 1/2 1 minus cos 2 theta, close that, close that, close that, all squared d theta. And we're just going to beat this thing to death with the algebra hammer. When I square this whole apparatus, I'm going to get 1/4 times, and I'll pop the 1/4 out of the integral. What's left inside is 1 minus cos 2 theta squared, which I then need to FOIL out. Okay, Lucas, do try to keep up. Definitely worthwhile to work on the homework, get yourself caught up, and then email me. If you can't make the office hour today, email me to arrange a separate office hour. That way we can make sure we're all on the same page. We'll have a little office hour some other time in the week. So I'll have 1/4 times the integral, and now I need to FOIL this big thing out. That's going to be 1 minus 2 cos 2 theta plus cos squared 2 theta. All integrated d theta. And I could at this stage split the integral up, but I'm not going to. This is what I mean when I say ideal notation. I know that I need to use another identity on this thing, and I know that that's going to give me another constant term. So rather than splitting that up, I'm going to leave these together so that I can combine this 1 with the constant term I'm going to get from that. I can keep my 1/4 out front. Integral 1 minus 2 cos 2 theta. And then cos squared of 2 theta is 1/2 1 plus cos 4 theta. Like this. Wait, did I read that right? You get the 1/4. Yes, yep. Yeah, so the 1/4 came from squaring the 1/2, and then what's left is the square of 1 minus cos 2 theta. Then I FOIL that out, and I realize that I'm going to have to use my identity on the cos squared 2 theta piece here at the end. So now I've done that. This is going to give me another constant term from the 1/2 times 1, which I'll be able to combine with this guy. So altogether, I have 1 minus 2 cos 2 theta. Distributing this 1/2, I get plus 1/2 plus 1/2 cos 4 theta d theta. And now this one and this 1/2 add up to 3/2. So this is the integral of 3/2 minus 2 cos 2 theta plus 1/2 cos 4 theta d theta. And now there's no powers left. Everything is stuff I know how to integrate. 3/2 integrates to 3/2 theta, or 3 theta over 2. Minus cos 2 theta integrates to sine 2 theta over 2. the 2's cancel. 2 cos 2 theta integrates to just sine 2 theta. Right? Cos 2 theta on its own would integrate to sine 2 theta over 2, and this 2 cancels with the 2 that would show up downstairs from the integral, from that little micro u sub. Plus cos 4 theta integrates to sine 4 theta over 4. So we'll have plus 1/8 sine 4 theta. And then our plus c. And then lastly, we could distribute the 1/4. Like so. All right, this is the nicest way to write out the solutions for these problems. Yeah, the 3/2 is the funny piece. So this 3/2 came from this 1 plus this 1/2. And then, so 1 plus 1/2 is 3/2. And then when you integrate a constant, d theta, you just get that constant times theta. You could write this as 3/2 times theta if you want to. I just like how 3 theta over 2 looks more. But you could just write it as 3/2 theta. But I combined the 2 constant terms here to get this single constant term. Compare this to the problem we just did, where at the very end, I had a 1/4 theta minus a 1/2 theta. Both of those came from integrals of constants. Instead of combining them at the end, I combined them here inside a single integral. It just looks better, it flows better. There's nothing wrong. You could split up the integral at this step if you wanted to, but then you'll have some like terms that you need to combine at the end. And I would prefer to keep everything together. That's what I meant when I said I'm going to do this as efficiently as possible, as nicely as possible. This is kind of the ideal notation. Okay. Any questions on this particular problem? Where did this come from, or why did we do that like that? How come this identity? How come not that one? Anything at all like that? As you solve your homework problems, try to write them like I'm writing them here. Try to get your notation to look as much like mine as you can. This sort of thing will help you with your organization, and you'll be amazed how closely related the neatness of your work on the page is to the neatness of your thoughts. And one easy way to get your thoughts to become neat, organized, reasonable, correct, is to make your hand be neat, organized, and correct. And then the thoughts will follow. The overall strategy here, I look at this integral and I say, oh, well, that's a sine cosine integral where both of the powers are even. The power of sine is 4, the power of cosine is 0. So I know I'm going to have to use my half angle identities. In order to use the half angle identity, I need sine squared, right? They both start sine squared, cosine squared. So in order to do that, I write this as sine squared squared. I'll address the question in the chat in just a second. Now that I've rewritten this as sine squared squared, the sine squared inside I can replace using my half angle identity. Since the original sine squared here is being squared, I have that whole half angle identity being squared. Now I give that 1/2, or I give that power of 2 to this guy and to this guy on their own, because those two things are being multiplied. 1/2 squared is 1/4. and that's a multiplicative constant, so it will come out. And then I've got the other piece, the 1 minus cos 2 theta all squared. I FOIL out 1 minus cos 2 theta squared. This is my result of the foiling. And then I recognize this piece as needing more half-angle shit. Why? Because it's an even power of cosine, and there's no signs here for me to play with. So this guy, and for the same reason I said this needs to start with half-angle, this needs to start with half-angle. I replace him with his half-angle equivalent, which is this. The 2 theta becomes a 4 theta. You can really think of it as a double angle identity. Same thing, right? Half angle and double angle identities are the same fucking thing. That leads me to here. The 1/4 comes along for the ride. The 1 minus 2 cos 2 theta comes along for the ride. The only difference from here to here is this. Then I distribute this 1/2. 1/2 times 1 is 1/2. 1/2 times cos 4 theta is 1/2 cos 4 theta. And then I look at what I got. Do I have any like terms that can be combined here? The answer is yes. I've got 2 constant terms that can be combined. 1 plus 1/2 is 3/2. This just comes along, this just comes along. And then my antiderivative step. Antiderivative of a constant is that constant times theta. Antiderivative of cos 2 theta is sine 2 theta over 2. 2 times sine 2 theta over 2 is just sine 2 theta. So the antiderivative here would give me a 2 downstairs, which cancels with the 2 upstairs. And similarly, the antiderivative of cos 4 theta will give me a 1/4, which I combine with the 1/2 into a 1/8. So antiderivative of cos 4 theta is sine 4 theta over 4, which when multiplied by 1/2 is sine 4 theta over 8, or 1/8 sine 4 theta. And then lastly, I distribute. So then the other question from the chat, one person asked to just go over the whole problem quickly. And then somebody was asking, yeah, Dalton. Understand how something like the integral of cos 2 theta is 1/2 sine 2 theta, but why is the 1/2 there? Dalton, could I ask you to clarify? Let's number the lines, right? Here's line 1, 2, 3, 4, 5, 6, 7. Because we have so many lines and so many 1/2s, you're asking about the 1/2 from which line, Dalton? Okay, so an in general question, which shows up in step 6. Is it this piece to this piece that you're asking about, or this piece to this piece? Let's call these pieces 1, 2, and 3. In line 5 to line 6, are you asking about piece 1, piece 2, or piece 3? Oops, sorry, my chat. There it is, piece 2. Okay, let's come to the side and do the piece 2 integral. So piece 2 from lines 5 to 6. I have integral 2 cos 2 theta d theta. So this is one of these micro u sub things. If I let u be 2 theta, then du is 2 d theta, which means 1/2 du is d theta. So this would be 2 integral cos u times 1/2 du. I can pop the 1/2 out and I get 2 times 1/2 integral cos u du. These cancel. Integral of cos u is sine u plus c, which is sine 2 theta plus c. Does that help? So there's a 1/2 coming from the u sub that cancels with the 2 out front. That's all. So they're good questions, and it's the perfect time to be asking questions like this. You don't want to be struggling with this in the homework. You want to struggle with it now, where we're here to talk about it. So what else? I know other people are thinking other things. What else? No bad questions here, guys. What else are we worried about? So Nicholas, well, I think you have the right idea that language isn't the language I would use to describe the process, because power function means something kind of specific. But if you're dealing with a sine cosine integral where both of the powers are even, then you will apply half angle stuff. Then distribute and simplify as much as possible. Any powers of trig functions which remain will necessarily be even powers again, which means more half angle stuff. So what we do is we apply, if you've got only even powers, do whatever is necessary, like this step to this step, to apply the half angle identity. Then yeah, multiply everything out, simplify, combine any like terms, and look out for other even powers of your trig functions. That will be more half angle identity stuff. Multiply out, simplify, and keep going until all the powers are gone. Once you get down to something like this, where all the powers are gone, like in our line 4, you know that you're done with your half angle shit. Then combine all your like terms and integrate, and it should just be micro U sub stuff from there. So that's the general strategy for even powers. You just beat the shit to death with half angle identities until all the powers are gone. It's not pleasant. It's not. I'm not going to pretend like it's pleasant. These are my least favorite integrals from this section, but they're important. So if at least one of the powers is odd, life is pretty good. We know we'll be able to get there just with a simple U sub. We'll need to use Pythagorean identities, but it's always manageable. If neither of the powers are odd, though, we have to do this shit. So that's the overall strategy, right? Make sure you have these words written somewhere in your notes. When you're dealing with sine cosine integrals, if at least one of the powers is odd, your goal is to do a substitution. The way you do that is by grabbing one copy of the odd powered function. If they're both odd, you got to pick one. Set it aside with the differential, and then substitute for whatever the other guy was. The way to make that substitution go through, this will require Pythagorean identities. Because you're going to still have copies of the other function. If you substitute for sine, you're still going to have copies of cosine floating around there probably. So you'll need to rewrite those cosines as sines using Pythagoras. But straightforward, simple U sub just maybe requires a little Pythagorean work. If neither of them are odd, that means both of them are even. And in that case, we use these identities. You can call them half angles or double angles, I don't care. But you use these identities until all the powers are gone. Then you can integrate. And those integrals will always be micro U sub integrals, just sine 2 theta, cos 4 theta, that sort of stuff. Everybody got this in your notes? I'll give just a few more seconds. If you get stuck, this is what you should look back at. So our next topic, secant tangent integrals. The sine cosine integrals, at least in the nice case where one of the powers is odd, what makes those work is that the derivative of sine is cosine, and the derivative of cosine is almost sine. So that allowed us to play that game where we set aside one copy of one and substitute for the other. The derivative of secant is not tangent, and the derivative of tangent is not secant, but they are related to each other. So similar tricks will work, just not the same exact tricks. Unfortunately, these can get a little bit unruly. So I'm going to break these down into two cases as well. The first case is if the power of secant is even, right? The derivative of tangent is secant squared. So if the power of secant is even, then I can pull two copies of secant out to set aside with the differential, and what's left will be another even power of secant, which I can rewrite in terms of Pythagoras. So if the power of secant, m, is even, we're going to try to substitute for tangent. This means we're going to set aside two copies of secant with the differential to make that substitution go through, and then rewrite the remaining powers of secant in terms of tangent, using the secant tangent version of Pythagoras, which is tan squared x plus 1 equals secant squared x. Right? That's like the sine squared plus cos squared equals 1, but for tangent and secant. On the other hand, if the power of tangent is odd, I'm going to try to sub for secant. To do that, I'm going to have to set aside a copy of secant tangent. With the differential. This will require rewriting the remaining powers of tangent in terms of secant. Using the same identity. All right. Both of these cases are similar to the first case of the sine cosine integrals. In both of these cases, we're going to get everything done with a little substitution and the Pythagorean identities. You'll end up integrating a polynomial. It won't be bad. You may notice that these cases are not exhaustive. There are integrals like this that don't fall into this and don't fall into this. How do you fail to fall into this? Well, if m is even, then blah, 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 blah. So, okay, what if m is odd? Well, then I'm definitely not here. If m is odd, then I'm definitely not here. Well, what if n is not odd either? So if m is odd and n is even, I'm fucked. Then I'm not in either of these cases. If the power of secant is odd and the power of tangent is even, hold on to your balls and do the best you can. It's usually going to mean some integration by parts, and it's usually going to be a looping integral. Those are the hard ones. First, I want to show you how to do these. So just to make this list exhaustive, if m is odd and n is even, get ready for looping IBP. This is the scary case. Cross your fingers. Pray to whatever deities you like. Maybe write your senators for help. You know, standard disaster stuff. It's not going to be easy. So that's the rough case. But the first two cases are not too bad, and I want to get you comfy with those, and then we're going to focus on the third case Friday. So let's take a look at some secant tangent integrals that aren't awful. Remember, the integral of secant, we know. The integral of tangent, we may remember. So I suppose I should remind you before we dig in, the basic ones here. The integral of secant is a little bit weird. This guy on his own falls into the third case here, because the power of secant is odd, it's 1, and the power of tangent is even, it's 0. But this one we memorize. Remember, we multiplied by secant plus tangent over secant plus tangent. And at the end, you get the natural log of the absolute value of secant x plus tangent x plus a constant. Does anyone remember how to integrate the tangent function? This is a Calc 1 problem, but I think a lot of folks forget it. Not quite. Yeah, we've got a few conjectures here, but we don't quite have it. So secant squared is the derivative of tangent, not the antiderivative. So Gustavo, you're half correct, but secant squared would be the derivative, not the antiderivative. Dalton, 1 over 1 plus x squared, that's the derivative of the inverse tangent function. So that's not it either. The trick to getting this, Simon's getting closer, is to write tangent as sine over cosine and then to make a little u sub. Mariano made the same conjecture that Dalton made. 1 over 1 plus x squared is not the integral of tangent. That's the derivative of arctan, which is different. So I'll show you how to do this real quick. It's very fast. We rewrite tangent as sine over cosine. And then you substitute for cosine. You let z be cos x, dz is negative sine x dx. So this becomes integral negative integral 1 over z dz. So you get out the negative ln of cos x plus c, which you could write as ln of secant x plus c, because this negative could come inside as a power, and the negative first power or reciprocal of cosine is secant. So either of these is fine for the integral of tangent. Make sure you remember one of them. I think the negative ln of cos x is the most natural way to remember it because that's what you get right away from this substitution. All right, what about the integral of secant squared? Who differentiates to secant squared? Tangent, yeah, good. Okay, and we're going to do one more kind of silly one like this, although I have stumped students with this in the past. Tan squared. This one's a little funny, but it's not funny like the integral of secant is funny. It's not bad. Not quite secant. Derivative of secant is secant tangent. But if I use Pythagoras, tangent squared is the same as secant squared minus 1. That's an identity. And then the integral of secant squared, I know. The integral of 1, I know. The integral of secant squared is tangent. And then minus the integral of 1 is just x. So that guy is a little bit funny. These are the things that we need to have solid in our brain before we attack problems of this type. So these are kind of the basics that we need for the secant tangent integrals. And they're a little bit harder than the basics for the sine cosine integrals. I'll acknowledge that right out of the gate. This last one, it's okay if your brain didn't come up with this right away. That's all right. It's kind of a weird thing. But tan squared is secant squared minus 1, right? That's just the identity. And then the integral of secant squared is tangent. The integral of 1 dx is x. So we get tangent x minus x. So these are the basics that we need to know. Make sure you get everything that's on this page nice and clear in your notes. Okay. If there's any one part of this that you want me to zoom in on or explain or talk about a little bit, please let me know. With that in mind, we are ready to dive in. Any little questions on this stuff? Well, I mean, I'm not a religious person, so I don't actually pray, but remember that the integral of secant cubed was one of our looping IBP problems from last week. And that is a case where the power of secant is odd and the power of tangent is even. The power of tangent is 0 there. So basically, it's just that the stuff that works really nicely in the first and second cases doesn't work at all here. We're kind of in trouble here. The obvious strategies, like use trig identities and try to substitute, they just won't ever get you anywhere if m is odd and n is even, which means we're going to need to try some more sophisticated methods. And the only other sophisticated method we have is integration by parts. And it turns out that those problems are always looping integration by parts problems, which I know most people find pretty challenging. So that's the reason I said, you should pray or do whatever there. Let's take a look at a tame version, though. Let's take a look at something that's not too bad first. All right. So tangent to the 5, secant to the 7. So here the power of secant is odd, and the power of tangent is odd. Okay, so is the power of secant even? Nah. Is the power of tangent odd? Yeah. Okay, so I'm going to take the second approach here. Since both of the powers are odd, I can very easily set aside a copy of secant tangent. So I start by rewriting this as integral tan to the 4th theta secant to the 6th theta times secant theta tangent theta d theta. Because I'm thinking I want to try and substitute for secant, which means I'll need a secant tangent for the differential, because the derivative of secant is secant tangent. That means everything else that's left over needs to be written in terms of the secant function. In particular, this 4th power of tangent needs to be written, needs to be written in terms of secant. So in order to do that, I write tangent to the 4 as tan squared theta all squared. Secant to the 6 can hang around because he's what I'm going to substitute for. That'll just be z to the 6. And then secant theta tangent theta d theta still hanging on. This goddamn dot can focus. There we go. I got you. All right. So my next move here is to rewrite tan squared in terms of secant. Tan squared plus 1 equals secant squared. So tan squared is secant squared minus 1. There I'm using the Pythagorean identity. Right? Now that I have this as a bunch of stuff only involving the secant function times secant theta tangent theta, I can make my substitution. I will let z be secant theta so that dz is secant theta tangent theta d theta. And so my integral becomes z squared minus 1 all squared times z to the 6 times dz. And the miracle is that this is a polynomial, right? All of the nice trig integrals result in a polynomial. You have to do some substituting and some other stuff. The ones that are not nice are the even powers of sine and cosine, where both are even, and then the secant tangents, where the secant is odd and the tangent is even. Everybody else, you should be able to get into a polynomial with some combination of substitution and trig identities. From here, we FOIL it out and then distribute. So I'll have z to the 4 minus 2z squared plus 1 times z to the 6 dz, which is the same as z to the 10 minus 2z to the 8 plus z to the 6. And then I can find an antiderivative just using my power rule. Z to the 10 will integrate to z to the 11 over 11 minus z to the 8 will integrate to z to the 9 over 9. So that's 2z to the 9 over 9 plus z to the 6 will integrate to z to the 7 over 7. And at this stage, I start writing my plus c. And then finally, we go back to our original variable. Because it's an indefinite integral, we have to do that. I get the 11th power of the secant function over 11 minus 2 times the 9th power of the secant function over 9 plus secant to the 7 theta over 7 plus a constant. Okay. not too bad. Not too bad. It's a lot like the sine cosine integrals, where at least one of the powers is odd. Questions on this guy? Yeah, no, not the end of the world. All right. So let's look at one of the other cases. Here we had an odd power of tangent, right? That's what allowed this to go. What if I have an even power of secant? Here, the power of secant and the power of tangent are both even. Yeah, no longer true. There is a certain amount of that here in Calc 2, where the elegance of your answer suggests correctness, but it's not always true. What's more, and I'm glad you mentioned that, Dalton, let's take a quick detour for a second. You don't need to write anything down, but just hear me. These integrals, many of them have solutions that can be written in different ways. So if you're reviewing your work or if you're solving practice problems and your answer doesn't look the same as the answer from WebAssign or the answer from the back of the book or the answer from wherever you're getting your answers, don't panic. It doesn't automatically mean your answer is wrong. Because these trig functions can be expressed so many different ways using trig identities, sometimes two answers can look very different but actually be the same. Indefinite integrals all have infinitely many answers. The way to check is to graph your function, use something like Desmos or Wolfram Alpha, and graph the answer that you know is correct. If they sit right on top of each other, then you know your answer is correct. But what's more, if they're vertical translates of each other, because of the plus c in the indefinite integrals, any vertical translate of the correct answer is also a correct answer. So don't panic if your answer doesn't look as pretty as the answer in the book or on WebAssign or wherever. Just graph the two and see if they are vertical translates of each other or not, like x squared and x squared plus 1 would both be correct answers to the integral of 2x. All right. Power of secant is even, power of tangent is even. So what do I do? What am I trying to substitute for? Yeah, Dylan asked a good question. It's possible to be both of these. And if you have something that satisfies both of cases 1 and 2, they're not exclusive. You can have an even power of secant and an odd power of tangent, then you can do either. Kind of like when both powers of sine and cosine are odd, you have a choice. In that case, you would have a choice also. I would take a look at either way and try, see which way leads to the nicer integral. Here, I do fall into case, I forget which one was what. Yeah, I fall into case 1 and not into case 2. So the only path for here is to try and substitute for tangent. So I'll set aside 2 copies of secant. That'll give me secant squared theta, tangent squared theta times secant squared theta d theta. I do that so I can let z be tan theta, which means dz is secant squared theta d theta. And under that substitution, my integral becomes, well, I guess I should do one more thing before I do that. Since I'm subbing for tangent, I need to write this secant squared in terms of tangent. Tan squared plus 1 is secant squared. So I get tan squared plus 1 times tan squared times secant squared theta d theta. Now I'm ready to plug in that substitution. Oh man, I got so many fun applications for this section. If you want to talk about applications, I got you all day. But let's do this first. Fourier series, guys. Fourier series, the most important application of mathematics in the last 100 years, is all about trig integrals. So when I implement that substitution, I will get z squared plus 1 times z squared dz, which can be written as the integral of z to the 4 plus z squared dz, which becomes z to the 5 over 5 plus z cubed over 3 plus c, which finally becomes 10 to the 5 over 5 plus tan cubed over 3 plus c. How am I doing on time? Do I have time to divert a second and talk about applications? We gonna do it. All right. Yeah. I'm not sure if rocket ships for Mercedes, but oh wait, what's going on here? Yeah. Yep. I do this often, not quite daily. Many of the applications, so my world is number theory. Fourier analysis is actually very important to the type of number theory that I do, but I do it a little bit differently. Anyway, so let me show you something. No, it's on the desktop, isn't it? Where is it? There. All right. In section 7.2, there are some excellent problems, not there, here. All right, I don't know if my Zoom overlay is blocking your view, so let me move it like this. Down here, number 70, you see they talk about finite Fourier series. Most Fourier series are not finite, they're infinite. But it turns out that one of the nice ways to approximate a very complicated function is using a sum of simpler functions. So you add up a bunch of simple functions to approximate a complicated function. This is especially important for electrical engineers, right? Circuits, but not just circuits. Really, anybody who deals with oscillation, since circuits, especially LHC circuits or LRC circuits, are oscillatory in nature. They bounce a current back and forth. A number of circuits are built around those or out of those, and they all have this oscillating feature. Think about your alternating current that comes out of a wall. You may or may not know this. That's a sine wave. You don't have a positive and a negative in your wall socket. You have if you have 3 prongs, one of them is the hot, one of them is the switch leg, and one of them is the ground. The hot bounces back and forth between positive and negative all the time. It's an alternating current. That's what AC current is. Anything in the universe that is run on alternating current or has any circuitry in it that is based on the mechanics of alternating current has components which are necessarily described as Fourier series. Also, if you do any sort of audio engineering or sound work or anything that processes sound or anything that is sound-like radar, sonar, all that shit, all built around Fourier series. All electronics that have to do with sound, not just Pro Tools, not just the stuff your favorite DJ does, but your grandma's hearing aids, everything built around Fourier series. What a Fourier series lets you do is uniformly approximate a function. So I want a GIF. So you see the red function is going to get closer and closer and closer to the blue function. The red function is a Fourier series for the blue function. Even if your function is discontinuous, like here the blue function is continuous, so the red function gets on it right away. Even if your function is discontinuous, here you see the blue getting closer and closer and closer to the red. The blue is the Fourier series for the red. Also in number theory, if you learn 3 blue, 1 brown, Fourier series number theory. This guy's got some excellent videos on what Fourier series and Fourier transforms do. There is a number of whole fields of mathematics that have to do with this stuff. There's one of these that I really, really like. Let me get rid of the number theory part. Yeah. Another huge area of applications for these things is in solving partial differential equations. So if you have, oh, this is cute. Yeah, here he's getting this graph out as a complex Fourier series. So all of physics is about differential equations. Differential equations tell you how heat and force and energies interact with each other in the real world. The way you solve those things is with Fourier series. So applications here are endless. The way you calculate the coefficients in a Fourier series, like this. Now this is just called a sine Fourier series. They've eliminated all the cosine terms, but normally there are both sine terms and cosine terms, and they all come out of integrals looking like this. So trigonometric integrals, probably not just like related to applications, but maybe the most important application thing in all of Calc 2, besides probably Taylor series, which we're going to talk about at the end. So these trig integrals are the fundamental building blocks for Fourier series, which are themselves the fundamental building blocks for pretty much all of advanced applied mathematics. Now, I know that was a bit of a long tangent, and I think we might be a bit short on time here. I did see something in the chat, but my chat window doesn't want to come up, so give me just 1 second. Oh, there it is. No, of course, I'd be happy to extend anything. I did go through and clear out all of the extensions that I had Monday, and I looked, I think yesterday, yeah, I went through and cleared everything out yesterday. If you submitted something since then I will be in to clear those today. The only integrals here we haven't looked at are the nightmare case ones, then where the powers of secant are odd and the powers of tangent are even. I'm not going to solve it right now, but look back at your notes from integration by parts, and this is where we will start next time. We can look at secant theta times tan squared theta d theta, and we can look at like secant cubed theta tan squared theta d theta. These are hard. These are the ones that are going to require a lot of work. Namely, they're looping IBP problems. So we will tackle those. Of course, secant cubed on his own, we've already seen. These are the hard ones from section 7.2. So go ahead, dig into the homework. You got everything you need to do pretty much all of those problems. I think there's 1 or 2 problems like this in there total. All the rest are the things that we have covered thoroughly and looked at several examples of. I don't think you'll have too hard a time with this as long as you remember your trig identities and you're very, very careful. So I'm going to switch over to my office hour here in just a couple of seconds. Are there any questions before we get out of here? Dalton, I will look and see if there's an extension that I need to clear for you. Anything else that you guys wanted to talk about before class ends? All right. If you're interested in the applications for this sort of stuff, I really do encourage you to look at the 3 Blue 1 Brown videos on Fourier series. 3 Blue 1 Brown, my favorite math YouTuber for like fun stuff. It's still very educational. You can still learn a lot from it. but it's edutainment-y. You know, he's got really good animations. You develop a lot of intuition by watching his videos. He's great in general. Check him out. If you want to see anything about that, I strongly encourage it. All of his stuff, his Essence of Calculus videos are amazing. His Essence of Linear Algebra videos are amazing. His stuff on Fourier series, really, really good. He's also got a few fun things on number theory. So I definitely encourage you to check those out. But make your first priority getting through the, yeah, it's awesome. It's awesome. Make your focus getting through the homework. But then if you have any time and energy left after that, I strongly encourage you to check out 3 Blue 1 Brown. All right, I will end the meeting here. If there's anything you want to talk about, come see me in the office hour. If you can't make the office hour, send me a Canvas message. We'll schedule a separate office hour. But that's the way I'm doing it for now. So just anytime anybody wants to talk but can't come to an office hour, just send me an email or a Canvas message, and we'll schedule a different timed office hour for you, since there's no overlap between the different times people wanted. But otherwise, I will see you either in my office hour starting now or on Friday. I hope you guys have a pleasant rest of your day.